In the next hour or so, I would like to talk to you about deep neural networks. In the previous sessions, you've learned a lot about how to analyze EEG data. You've learned a lot about multivariate analyses, including decoding, classification, RSA. And I will here show you one example how you can compare EEG or brain data to particular models called deep neural networks in order to understand the brain a bit better. Now, this is not going to be a content talk about neuroscientific finding mostly, but a meta level talk where I really talk about what these deep neural networks mean and what their comparison to the brain means. So that brings me to the title, which is that I would like to talk about what these deep neural networks can tell you as scientific models about the brain. How can they be useful? Now, many of you likely know what deep neural networks are because they're all over the press, in public, in all types of layouts. But I will start with a short introduction of the very simplest case, what they are. I will tell you why they are so important right now in cognitive neuroscience. I will tell you about a current debate going on, which is about their value, because some people believe that they don't have value for neuroscience. Others think that they are the best thing that ever happened to neuroscience. And I would like to collect arguments for and against that and try to shed light on them from the bird's eye view. And this will give you a background to tomorrow's, I think, session with Cichy, who is going to show you on a very practical example how you can compare brain data with deep neural networks. Okay, so what are deep neural networks? Deep neural networks are artificial models which are inspired by the human brain. And I would like to explain to you what they are, going from their smallest unit to the whole thing. So the basic unit of an artificial deep neural network is something called a node, which is akin to a biological neuron. It gets multiple inputs, here as you see, the x1 to xn, and it weighs those inputs, like synaptic contacts do, that differentially affect cell potential. Now, it has a transfer function, which this is how the inputs are weighted and often combined. And this is just most often just a sigma, so a sum, modeling how the cell combines synaptic inputs. So it gets inputs and then it adds them up. Then it has an activation function, which determines the output given the input, something like a spike. So exactly like a neuron, you get inputs, they sum up in ePSPs and iPSPs, and if they, let's say, cross a particular threshold, then there is a nonlinear response, like a spike, or here in this case, the neuron would fire and activate, or it would not. So this is what an artificial node in a neural network is doing, and it's very much modeled after a neuron. Now, how are these nodes ordered? Nodes are typically ordered in layers. So, for example, here we have this input layer. This is the layer where things from the outer world would enter, let's say, the brain, for example, information coming from the eye, or if you want to build something equivalent for a computer, maybe the pixel values of an image saved on your hard disk. Then this information is processed by, so in the input layer, input neurons, and it's propagated by connections to other neurons, which are usually ordered in layers. And if these layers are not the input or the output, they're called hidden layers. Now, when each layer sees only the input from the previous layer, it's called a feed-forward network, because information comes in here and can only travel one way. If, for example, the connections would be going to the same neuron back or within one layer, it would be a recurrent neural network. Or if it was going back from one layer, like coming in here, going back, coming back, then it would be also a feedback or recurrent neural network. But pretty much everything we will talk about today will be feed-forward neural networks. Okay, so now we have, let's say, these layers. And the question is, how are these layers connected? Well, in one case, the neuron can be fully connected, where each neuron sees every other neuron in a layer. So as, for example, in this example here, this one neuron has connections to all the neurons in the input layer, so it sees everything. And in the next layer, like hidden layer 2, this neuron sees all neurons in the hidden layer 1. This is likely unrealistic, right? No neuron in the brain sees every other neuron. So it makes sense to put in some structure there today. And today's networks usually have a convolutional structure, which looks like this. This is a particular example from an old paper in 1998, but since then actually not much has happened. So what this network was doing is it takes as input pixel values, for example, like an image of an A, and every neuron has a receptive field like you would have in visual cortex that looks only at a particular part of this image. And it is a particular feature, so it responds to one particular type of information in the image. For example, I could say that in this feature map here, all neurons respond to edges oriented in this way. So this feature map is actually a lot of neurons that all respond to, let's say, oblique orientations, and they're going to be active whenever there's an oblique orientation like this or like that, and otherwise not. And you can have many different types of features, so you have different types of feature maps. Now here you don't have single layers, but you actually have feature maps in two-dimensional, not one-dimensional, because it makes sense. If you don't look at something which is one-dimensional, but something like an image, two-dimensional, you could also just order your neurons in a two-dimensional way. And because this is the simplest case, you have a feature map, which means that every neuron in here responds in the same way or responds to the same features. So for example, this neuron here responds to this oblique orientation, this neuron also to oblique orientation, just in different parts of the image. So what basically this amounts to is like pulling a window over this image, always with the same feature, and basically telling me where the feature responds to this. And this is called convolution. So basically sliding a short window over of this signal is a convolution. That would be a convolutional layer. Now, passing on from one layer, so this is the input layer, to the next layer, this would be the hidden layer 1, the feature maps are subsampled, meaning that they are becoming smaller. So if you go in with a 256 by 256, for example, sized input, it would be 128 by 128 or something like that. So you only take one value from the neighborhood, making the feature map of the next layer smaller, smaller, and smaller, while making the number of different features as you have larger, larger, and larger. So the more you move in the network, basically the smaller the image becomes, but the more different features you have. And features can be, for example, here like orientations or colors or things like that. And the idea here is that you're trying to build up something like, if you care about vision, about invariance. So, whether you present a letter here or whether you present a letter here, your brain always wants to know what letter it is. So the position doesn't matter. And by always integrating over bigger and bigger parts of the screen, you can get this invariance, for example, to where in the screen something is projected. Once you have gone through once basically your feature maps are very, very small, then it just makes sense to go into fully connected layers, and every neuron sees every other neuron. And this is the basic setup of a deep neural network as we have it today. You have input layers, you have convolutional layers, you have max pooling or some type of subsampling so that the maps become smaller, but the number of features grows until at some point you have fully connected layers. Now, how do these things learn, right? Because I just told you the things take something as an input, for example, the letter A, here printed as an image, and it's supposed to give us a particular output. For example, in this network, it would have something like, let's say, 24 different outputs. It actually had 10, but let's say 24 for the different letters of the alphabet, and it's supposed to say what it is. Like if you had a letter written and you would like to know, in handwriting, and you would like the computer to know where or to whom this letter has been sent, you would have to recognize the handwriting, and for every thingy coming in written by hand, like this A here, you would like an output digitally, like an A, B, C, D, wanting to know which letter it is. So how does this network know that this is an A and not a B? So what you do, and this is the trick with it, you actually start with completely random weights, meaning that every neuron is connected to other neurons in the way that the architecture tells you how to, but it hasn't learned anything yet. It's just completely random. So you basically put in this image and it's going to be randomly processed through the whole network, and it's going to give us some output. For example, here, whoops, it's going to tell us it's a B. Now, B is wrong, right? It's an error. So what we're going to do then is we're going to compare the real output to the desired output. This is supervised learning, meaning we know for, let's say, a subset of the data that this is supposed to be an A. We know that the network in the binning sets B. So we just tell it, oh no, it shouldn't be a B, it should actually be an A. So if the response of the network is wrong, it just tells us it's a B. We change the weights of this network, the connections, such a little bit, such as the next time that you see this A, the output is going to more likely to be an A than in B. And you do this by changing the weights in the layer at the very last layer. And then you propagate the changes back to the whole network by a technique called gradient descent, usually. And you do this by backpropagation. So you repeat this many, many times for many, many different images until at some point, if the network has learned, if you see an A, actually the network tells you, aha, in this image, there was an A. So the important thing to take from here, if you didn't get technical details, and that's important, it is that we do not tell the deep networks, the neural networks today, what features of the image are important to the task, but the deep network learns the features itself. You define the task, for this image, tell me it's an A. You train the network a lot, and it just finds whatever it needs to find to do the task in this image. It's not that you hand engineer, but you think like, maybe this part of the image is very important, or this junction here, and this should be coded. No, you leave that completely free. The network can use whatever it can use in the data set to learn what it has to learn. So why are we here today? What made deep neural networks so important? They've been around since the 1950s, or well, maybe 60s. And the question is, why suddenly in 2013, 14, 15, they became so much more popular? Well, there are several factors. The first is the failure of hand-engineered solutions to produce real-world ready systems. So a lot of engineering has tried to solve problems like image categorization or speech recognition. And all of these things worked in small toy domains, but if you put them onto a real world domain with lots of data, they all failed. And this was also so because the way that people thought that they can engineer how these things work just weren't the case. The second factor that was very important was actually gaming, because these neural networks use as a basic operation parallel matrix multiplication. And to do this efficiently, this is quite similar like if you have a graphics machine on your computer and you're playing around in the 3D environment, you're changing the perspectives and you're moving around. So this is basically matrix multiplication. And so GPUs were developed to do this for gaming, and we can just piggyback on top of this. So because these networks use very similar mathematical operations, we can use GPUs to train and run these networks, which makes them a lot faster. So to give you an example, I think AlexNet, when it was proposed 2012, needed something like 7 days on a GPU, and it would have needed something like a year or so, well, a bit less, on a CPU. The third factor that made networks so important was that large data became available. So these deep neural networks consist of units like neurons, and there is many of them, often millions and millions of connections. Now, if you want a model to learn from data, millions of parameters, you must give it very rich data. And where do you take this rich data from? If you just have a small database, like let's say 1,000 images or 10,000 images, that's not enough to constrain millions of parameters. But once you have the internet and you have Google and you can search images, you can build up databases like ImageNet, which for example had a challenge with 1 million images in 1,000 categories. And that is then actually enough to train such networks. Actually, one of the failures of those networks in previous times, like the 80s, was not much of these networks was different, but there just wasn't the data to train them. And the fourth is, something has happened since the 60s or 80s. There's been a lot of tricks that were put into making these things work, but this is more tricks rather than a radically new theory emerging. So why are these so important? Well, DNNs tackle very important cognitive functions that are also important for us as cognitive scientists. So for example, they are very successful in object recognition. That was, I think, one of the first demonstrations that a neural network trained to categorize 1,000 different categories did pretty well and better than any other existing algorithm before that. And actually right now on this image data set, the performance of the network is equaling human performance. You've maybe heard also from the press, Google's AlphaGo playing the game of Go, one against the world master. And this is a task of planning, which many people also believed such deep neural networks couldn't do. It can also solve questions of control. So for example, if you're playing Pong, there's two players and there's this ball going back and forth, you have to learn where to move this lever. And you can actually train such a neural network only from the input of the pixels on the screen and whether in the end it won or not to move this. And also similarly, if you can recognize images as a 2D plane, you can also transform, for example, language in the time frequency domain, and you can do natural language processing. And deep neural networks are doing very well on natural speech recognition. DNNs do not only tackle important cognitive functions for us, but they also used to investigate human behavior. So for example, they can predict where you're going to fixate an image better than I think any other algorithm. So here on the left, for example, you see an image and these dots are where people usually look. From this, you can get the human gold standard. And then you can show that a deep neural network, for example, here deep gaze 2 at this time point is approximating this gold standard better than any other algorithm. Similarly, deep neural networks can also predict human shape similarity judgments. So if I give you those images and I ask human beings to order them by how similar they are, then they are going to order them in such a way that these categories like spikies, smoothies, and cubies end up in different parts of the space. And this is how the perceived space of human beings is in the middle. And this is how GoogleNet, a deep neural network, does it. So it's mirroring more the perceived qualities of these images rather than, let's say, the physical properties as defined by the pixel values, which again makes it an interesting thing for cognitive neuroscientists. Now you've also learned that, and then people have thought, okay, so if these networks are so, they have similar behavior to humans, and they can do tasks that humans supposedly do and no other algorithm can, it might make sense to compare them to human brains. And they've done this, for example, here I showed this for representational similarity analysis. I won't go into detail here because you've learned about representational similarity analysis previously, but basically one thing you could do is, you show many images to, for example, a deep neural network. You show it to human beings while you record MEG or EEG. You show it to human beings while you record fMRI. Then you transform, as you've learned, these activations in these different spaces into RDMs, which capture the representational geometry in there. And then in these spaces, you can compare these things with each other. So by comparing, for example, EEG and MEG with DNNs, you get time courses of when parts of the network predict brain activity or where in the brain they do so. And actually, this has proven pretty successful. So DNNs have been used to investigate the biological brain, and they've shown to predict visual representations and the hierarchy in space and in time. So in space, for example, this is an example where people have compared a deep neural network trained on a visual task categorization to representations in the human brain. And they've shown that the network layers, which are closer to the pixels, explain brain activity in early brain areas. And the more you move up in the hierarchy of the network and the layers from layer 1 to layer 8, the higher you also move up in the hierarchy of the human brain, showing you that there is this spatial correspondence in processing stages. This does not only hold for vision, it also holds for auditory stimuli. So for example, DNNs predict auditory representations, DNNs that were, I think, trained to predict the genre of a particular musical piece. And they also do this in a hierarchical manner, that early layers predict early auditory areas, and the further you move up in the network, the further you move up in the hierarchy of the human brain. So there is this correspondence between these two things, which is very exciting, because before that, we never had such a model which would behave in this way. You can also use this, and now we come a bit more specifically to EEG, to investigate the biological brain in time. So deep neural networks have been shown to predict visual representations and the hierarchy in time using MEG and EEG data. So for example, again, looking at a deep neural network for object categorization, which had 8 layers. You can ask when in time do representations in the brain emerge that have similar representational structure like the deep neural network. And here you plot the time with respect to when an image was shown, and here how similar brains and DNNs are. And these are the 8 curves for 8 different layers. And then the first method basically is, yes, all of these layers actually do predict brain activity. So they are similar. And now we've also seen in the fMRI, well, early layers of the deep network explain activity in early visual areas and late DNN layers in higher visual areas. And if there is like a stream of information through this, this should also be the case in time, that early layers are activated later and later layers later in time. And this is what we find. So if you plot the peak, when you find the maximum correlation between the deep neural network and brain activity, you see that there is a mild but positive correspondence, that the higher you go up in the hierarchy of the deep neural network, the later it predicts brain activity. Now, these findings were around 2015, 16, 14 or so, and they've created a lot of excitement, but they've also created a heated debate. And both sides actually seem to make points that seem reasonable and deserve to be taken seriously. And I would like to go through different points that have been made on the debate about how to judge actually this practice of comparing deep networks to human brain activity. So the first point of heated debate was the overall potential of this. So critics of this approach said, look, there are so many limitations what you're doing. For example, there is a divergence between what deep neural networks and humans can do. Okay, deep neural networks can do interesting things, but they are still very, very limited to single tasks, and the human brain can do so much. So, therefore we need a different approach. These deep neural networks get you nowhere. Whereas the endorsers of the approach said, no, this is an unprecedented opportunity. We never before had models that ever predicted brain activity with such high correlation measures, let's say. And therefore, this is just a starting point. It's a feasibility demonstration from which we will see a new convergence of cognitive science and artificial intelligence. Second, the critics had said DNNs may predict brain activity. We've seen these nice images on the on the human brain and over time. But what do they explain? It's one thing to predict brain data. It's another one to say what is happening there and why. Whereas the endorsers would say, well, wait, deep networks do give explanations of different kinds. And I will get into what these explanations could be in this talk. Third, a common criticism was that deep neural networks have millions of parameters and features that they learn by themselves. So we have not set them a priori. So we don't know what they are. So basically they are something like a black box. We don't really know why they're doing what they're doing. And it's also part how each part of this contributes to the big whole of, for example, reaching the task that the network does. So what do we learn from comparing something which we don't understand, the brain, with something else we don't understand, an artificial model? Now, I think the endorser said, well, we agree that the models are not fully understandable at the moment, but I think there's a lot of potential to make them understandable. And I will tell you a bit how that can be done. Another point was biological realism. The critics say, these deep neural networks, artificials, they've been inspired by the human brain, but there is an infinite amount of ways in which they differ. And this is of course true. They are made in silico. They are very simple. They have nothing to do with real synapses or real axons or real action potentials. So how can this ever be a real model of the brain if it is so far away, if it's so idealized? Now the endorsers say, well, we are not very much impressed by this because abstraction, idealization, making things simple is basically essential for modeling. Every model is an abstraction of something, otherwise it would be just a copy. And also that today's networks are just a starting point, which we might then over time want to improve. And finally, people have argued that this deep neural network use is unscientific because it's untheoretic. Because what basically has happened is, oh, we got these networks in computer science. Let's take and compare them to human brains. Oh, they're similar. Yes, okay, but where's the theory? Why should we have done this? Whereas the endorsers would say, we don't care where the network is coming from or where the idea is coming from. All it What we should care about is how well it predicts or how well it explains. Now, okay, so if you have all these pro and contra arguments, it's a question, so what do you want to do? Do you want to work with deep neural networks or not? Should you fund such research? Should you not fund such research? Should you put your career in this? Or should you say that this is just nonsense? You should stop with it. Now, one way of solving this is just, to wait and see what history tells you. But if you are part of this history, I don't think that that's a good idea. So one thing I would suggest is that we just take a step back and evaluate the situation from a bird's eye view, from philosophy, and try to see what models can actually do for us. And I would like to do this in 4 parts. First, I would like to talk about model nature. So basically, what models in science are, or rather, what models are there in science? And I would like to talk that there is a plurality, a diversity of models. And I would like to talk about the origin. Then I would like to talk about how models play an important part for solving the 2 major goals of science, namely predicting things and explaining things. And prediction is where you use models akin to technology, use as a tool or as a benchmark. And for explanation, where you actually use models like a theory, where you provide an explanation. And finally, I would like to close with what I think is an overlooked but a fundamentally ubiquitous practice in science, that we actually do use models such as DNNs to explore and as a starting point for new theories. Let's go into the first. Let's talk about model nature, what scientific models actually are. And I would like to do this by making claims. And you can agree or disagree with those claims, but at least those claims will make one particular position clear that you can relate to. The first claim I would like to make is that we need many models, and would like to argue for this from so-called theoretical desiderata. Desiderata is what you want a model to have for theoretical reasons. And I would like to follow a particular claim that's been done that, let's say we want a model to have these particular values. One is precision. A model should be exact in its outcome. So, you put something in, you get something out, and you want it to be as precise as it can be in input and in output. You might also want a model to be realistic in the sense that it should work similarly to the phenomena that you're trying to model. A third virtue it might want to have, it should be general. So when you're looking at one particular part or entity, it should also generalize to another entity which is of a similar kind. So if you have a model of one fly, it might want to predict another fly. Now, the problem with such theoretical desiderata that people have to their models is that there's a trade-off between all of them. So for example, let's look at generality versus realism. If you have or maybe generality and precision is simpler. Let's say you have a model which is very general. It models all human beings very well. Then it models the mean of all human beings. And then it cannot be very precise, for example, for any single human being, because it wouldn't be general then anymore. A model of only Radek is modeling Radek and not Radek and Maria. And a model which is between Maria and Radek is not a good model of Radek or Maria either. So you can have either a very precise model of Radek or Maria, or you can have one which hits them both in the mean, but you can't have them all. So therefore, there's always this trade-off between those different values. Now, not really always. If you have let's say a target class, or you try to explain stuff which is homogeneous, basically all of its members are exactly the same, like atoms in a gas, then you can have all 3 things at the same time. But cognitive phenomena and cognitive beings are not homogeneous, because we are diverse. We are the result of evolution and experience. So there will never be one perfect model to fit everything. You will always need many different models to fill the many different theoretical desiderata you have, like precise models, realistic models, or general models. The same claim I would like to make from non-theoretical desiderata. Non-theoretical desiderata are basically stuff you want a model to be not for theory reasons, but for other reasons. And to make this clear, look at a contraposition. So let's say you could have access to the perfect brain model. You know, it's like the brain in all aspects, whatever you want it to be, just whatever you ever wished for. But unfortunately, it's incredibly slow, it's hard to evaluate, and it's ethically restricted, like, for example, the human brain is or a primate brain. Or you could have an inexact model that is very fast, easy to manipulate, and ethically unproblematic. You can smash it with a hammer, you can do whatever you want with it, who cares? And like a deep neural network. So which one would you like to have? Well, it depends on your goals, right? But many often you're going to say, I don't want this perfect one because, you know, I'm going to test my theory and my PhD is going to be over before it has run through once. I can just look at this imperfect thing and do 10,000 things to it and try to understand it much better. So there often, you know, non-theoretical desiderata take precedence over what you want by theory. And actually deep neural networks appear very attractive on these non-theoretical desiderata, maybe more than on the theoretical ones. The second claim I would like to make is, well, that the best models are actually diverse. And the question that I would to put to you is, okay, I've said that we need many different models for the many different desiderata, practical, non-practical, generality, realism, and all the others. So then you can ask the question, given that we need many models, will they all be of the same kind? So will they all at some point in history be deep neural networks, or they will be all different types of models that there are in this world? And it's hard to say, right? I mean, if you don't have psychic powers and you know the future, you don't know what's going to happen next, but you can extrapolate from history. And I would claim that in any branch of science, at any degree of maturity, whether it's neuroscience, like a new branch, or like immunology, which has been around 20, 30 years more, or physics, which has been around 2000 years more, there have always been models of different kinds. Never in history have we ever come in any kind of science to a state where there was only one type of model to which all other models reduced, and now we only use that. So therefore, I would say deep neural networks will have a place in this diverse set of models in cognitive science, but whatever is going to happen, they are just going to be one part of it. So it's not a debate of, oh, let's stop do anything else, let's only do deep neural networks. It's just that they will have one place among many other things. And then the third, I would like to claim, and this is the question about origin, is it important that these things were not derived from theory, that actually no, the origin of models is irrelevant? So, you know, a common view about models is like this. You have a theory, you made it up from something, experiments, lots of history, whatever. And then you think, okay, I want to test this theory, so I built a model from it to test or instantiate it. Now, because deep neural networks were not derived from a theory about the brain, they are inspired by it, but they were built for engineering purposes to make computers see and understand language or speech. So they are not proper theoretical models, because real models should come from theory to test them and not from somewhere else. And I would say, no, that's not the case. And the argument is a reality check from scientific practice, basically looking at how scientists make models. And if you look at how scientists make models, and you can think about if you ever use models in your own research, models are rarely reduced straightforwardly from theory. It's not that there is this theory and then by logical deduction, you get a model which does something from it. People that build models, you know, when you look at it, it's more art than logic. There is a element of creativity coming in that's not dictated necessarily by anything you previously knew. There is no set of rules. You know, if you ask me, how can I build a better deep neural network of the human brain? I don't know. There is no rules. It's not like chess where you can make a couple of moves and that's it. It can come from nowhere and everywhere. It's never written down. So, and again, non-theoretical desiderata are relevant. What makes a model a good model might be that you can run it fast on your computer and get it done rather than something else. So from this, I would say that the origin of a model for its scientific value is completely irrelevant. And therefore, deep neural networks being hijacked by cognitive science from other fields is just totally fine. It's basically to leave you with an image. It's like in ready-made. You know, you take a urinal, you put it in the museum. It's art. Okay. You take a deep neural network made by computer vision. It becomes a model of the brain because you use it in that context. You know, you don't need to derive it from some deep thinking about the brain. If it works, it works. Okay, so that closes the first part on model nature, where I talked, you know, that I think there will be different types of models necessary in explanation. Deep neural networks will be one part of them, but not the overall goal or only one there, and that the origin of where things come from is completely irrelevant. So deep networks and their comparison to brains is actually doing quite fine. In the second part, I would like to talk about the first goal of scientific practice, which is prediction, where we try to use models or science to predict the state of the future. So which means that we use networks as tools or as benchmarks. The first way that I would like to claim that deep networks are useful for science is that they can be used as a tool for a practical aim. And this has nothing to do with explanation. So forget about explanation for the time being. Let's assume, and this is just a hypothetical case, but it makes the point very well. Let's assume you unfortunately have a stroke in your visual cortex and you are cortically blind. Like you, for example, see here, you know, that's a stroke, and therefore you can't see anything in your left visual field. And then you ask your doctor, okay, what can be done? You know, can you give me my sight back? And he's going to say, you know, there are these deep neural networks. They've been shown to predict brain activity really well. So maybe we can put electrodes into your brain, which, you know, we're going to input into your brain the outputs of the deep neural networks as a stand-in, as a prothesis for your brain. Would you then tell the doctor, but I don't want this because I don't know how a deep neural network works? Who cares? Actually, for most medicine, you don't have the slightest idea why the medicine works. It was just found by serendipity, by chance. Now here it's a bit better, but still you don't need to understand the artifact for you to do the job. And therefore, for example, it can be a very useful tool for prediction of brain activity in a context like medical application without any recurrence to explanation. A second way how this might work is that you could actually use it for experimental design, optimization, or experimental control. So the idea is, so these deep neural networks predict brain activity really well. So can I use these networks now to induce a particular state of the brain that I want? Let's say I want a particular brain region to be in a state, and I can then just, you know, go backwards in my calculation and see which image would I have to show you so that your brain is in a particular state that I want it to be in. And this actually has been shown, and you know, that was, I think, a science paper, and this is a cell paper in monkeys, where monkeys were implanted with electrodes and they saw particular images. And then these deep neural networks were used in such a way that the experimenters asked, okay, please, algorithm, give me the image that would drive a particular cell to fire as much as it can. So they used a lot of sets. This is actually, you see here, this is the generation. So there was a development of this algorithm, and this is the response of a particular cell. And the green curve is how much this cell responds to, let's say, a random set of different images. And the black curve is the curve that tells you how well this cell responds to images that were predicted by the deep neural network to drive this cell into as much firing as possible. And it worked very well. So actually you can, in this way, find images that if they are shown to this monkey will drive this cell into overdrive, into unrealistically high firing rates, which again is not an explanation of what's happening in the cell, but you start having full control of it. So you use its power to predict brain activity to put this cell in the state in which you want it to be. And this is a feasibility demonstration that you can do this with you can do this very well. And this can be very useful. So for example, you have two regions and you want to know what the second region is doing while you're clamping the one in one particular state, because usually, let's say in a cognitive task, both are changing and interacting. So in this way, you could say, okay, I'm going to lock this one region to one particular state with my stimuli. So I'm going to look how this one relates independent of this. So it gives you experimental control, which you didn't have before. You can use it as a tool for experiments. Okay, that's the first way. You can just use it practically. The second is, I think you can use benchmarking by how well it predicts as a stepping stone for explanation. So the idea is, let's say you have a model which predicts brain activity well, but by now you have many deep neural network models. So you can actually say, okay, I'm going to compare all of them to a particular brain region or whatever you care about in your cognitive neuroscience research. And then you're going to make a list of which networks are really good in predicting and which networks are really bad. And this is going to help you because there's an infinite number of networks that you could look at. And it probably makes sense to limit yourself to things that already work very well. So once you make your list of how well things work just by prediction, you can pre-select models for further inquiry. You could also say, you know, I got these networks and all of these networks in the top have a particular property, and all the ones which are really bad in predicting the brain have another property. So maybe it's actually this property which makes them good models. So it gives you an idea and handle on how to go from just prediction to explanation. And third, it would also give you a good, let's say, baseline for explanations of complex function. And the idea here is basically, if you want to explain complex human behavior, you must provide models that do justice to this richness and that can explain complexity well. These models do. So you could say, okay, my competitors that low lying deep neural networks, I'm very happy to use whatever network you want, which is not a neural network, or whatever you want. But it should at least behave as good as my deep neural network, because what's the point of building, you know, great intellectually deep models which just don't predict anything? Because in the end, a model which is explanatorily great but doesn't work isn't worth much. So it's like, maybe these models by themselves are not worth much, but they're creating a floor for others, which they have to pass before they can say their models are important, so that we don't keep more and more time into testing unrealistic models, which never explain data. And there are actually websites that do take this up. So for example, there's a website called BrainScore. There was a recent Neuron paper published on this, which do exactly that. You know, the authors provide brain data. They provide information about dozens of models. I think you can you can submit your own data, you can submit your own model, and you can see how well you're actually doing with respect to particular brain data. And we've also done something like this. So we started the Algonauts project. It ran the time 2019. It will run again 2021 as part of the Computational Cognitive Neuroscience Conference. And it's not a website like BrainScore, but it's a challenge. So we will provide you with data, human brain data, and then you will upload outputs, if you want, of your model, whatever it is, deep neural network, anything other network, to explain brain activity. And we will just tell you how well you did or how well you didn't. And this is running over a particular time. And once you hit the deadline, there is just one winner. And this is the person that just explained brain activity best. So, you know, you can use the power of this prediction also to make this a community effort that uses the internet, where not everyone sits in the room and then publishes, and it'll take 3 years, but basically data is already there and you are immediately compared to everyone else. So we hope that this is going to foster and accelerate research. Okay, that was the second part of how I believe deep neural networks can help science by predicting, where we use them akin to technology, either as a tool where we don't care about explanation, remember the prothesis, or remember about predicting brain activity in a particular state and controlling it. You don't need to know how you're controlling, you just need to control it. Or where you try to go from prediction to explanation by benchmarking these deep neural networks to try to find out what makes some of them important and others not. In the third part, I would like to talk now about how these models can provide explanations. So how they can be used akin to theory for the purpose. Before I do so, I think I would like to more clearly tell you what the underlying grudge is that people have against deep neural networks when they are used in science for explanation. And this is something that has been often called the received view of how modeling is done, the mathematical theoretical modeling approach. And the idea is you have a particular phenomenon you want to explain. So you think about it and you identify a few relevant variables, usually a handful. And each variable is identified a priori with the part of the phenomenon modeled. So you know exactly what this variable is about. And then you use math to model the variables and their interaction. And then the changes in the model are directly interpretable as changes in the world because you know what each part is and you've ascribed mathematical relations between them. So whatever you change is going to be immediately interpretable and you know what you're doing at every step. Now, how do deep neural networks look against that? Well, deep networks do not have few variables, they have millions of variables. The parameters are learned by the networks, as we said in the beginning, themselves, and they are not set a priori. So we don't know which part of the world they refer to. So the relationship of the variables to the world is opaque. Therefore, you could say, from the perspective of mathematical theoretical modeling, this is pointless and the worst thing you could do, because deep neural networks are just a black box and you can't explain one black box by the other. And it makes sense, right? If you have this view of mathematical theoretical modeling, it just doesn't square. So what can we respond to this? And there's different ways how you can respond to this. One is you say deep networks change the game. They provide a different type of explanation, something you might call a teleological explanation, where teleological refers to telos from the Greek and goal or purpose, meaning that it's related to a goal, aim, or purpose. This is what you're explaining. So to make this clear, the question here would be, for example, if you look at deep neural network and want to know why does a unit behave such and such, you want to know what is this part doing, and it bothers you. There's a million parts and you don't know what this part is doing, so you pose the question. Then the answer is not, oh, because it refers to oblique edges at the lower left quadrant, and you tell me what basically it refers to in the world, but you say because it fulfills its function in enabling a particular objective, which is the overall objective on which this network was trained, rather than because it represents this or that part of the world. So by basically saying because it does whatever it has to do in this bigger machinery, this is basically its telos, its aim, and this is the explanation for why it's doing it. So if you just explain actually unit for neuron, you could make exactly the same explanation for what's happening in the brain. Why is this or that neuron responding in this or that way? Well, because it's fulfilling a particular function and enabling a particular objective, which you might know, but you might want to find about. And there might be actually nothing that can be put into simple words that this relates to in the world. It could be a very complex mathematical function that this neuron represents. And all it does, it plays its role, it does whatever it has to do to reach the goal of the whole algorithm. A second type of answer that can be given, which is very good, which is very different, is that the idea that this mathematical theoretical modeling is not fulfilled by DNNs is a superficial view. It's wrong. And DNNs actually offer this standard vanilla mathematical theoretical explanations. Because if you look at it at the right level, deep networks are fundamentally defined by only a handful of parameters, which I set a priori. So what do we set about such a network? Well, we set its architecture, basically how many layers it has, how many neurons in a layer, how these things are connected overall, like that there is convolutional layers or there is max pooling layers. We know the training material, the images that go in. We know the training procedure. So, when this output is more like a B and not like an A, then please look at the error between those and change the weight such that next time you see this A, it's more likely that the network says A. This is all fully specified. And we also know the objective, things like what this thing was supposed to learn. And at this level, these variables directly refer to phenomena in the world. You know, the training material is just a set of images on your hard disk. That's clearly what's there. The architecture is also clearly fully defined. So therefore, the model at this level is fully transparent and it's not a black box. Now you might say, yeah, okay, but I really want an explanation of what a single neuron is doing. And then you might say, well, you know, I can't give you this, but I just changed the game because the parameters I care about are very different from the parameters you care about. But why should I want to accept your wish to explain your parameters rather than mine, if my model is so much better in predicting the brain? So why choose these and not others parameters as being the most important for a scientific theory? I will cut the extension. A third claim you could do, and this is being most conciliatory, is that, okay, deep neural networks are actually opaque. We don't really know what the single features are doing, but these networks have a strong potential for post-hoc explanations. Basically, you can make them transparent by looking at how they actually work. And over the last years, and this is just a few examples, a huge amount of techniques have been developed to visualize and categorize the response properties of neurons in such networks. So for example, here you have an example of one thing. Here's another one where you can basically say that in layer 161 of a network, this unit actually responds to these types of faces, for example. So you can say, we don't know yet, but we can do in silico experimentation, as we also often do in the brain, and find out in this way what these things are doing after we've shown that they predict the brain well. And this is not such an outlandish practice. So for example, when we do biology, we often don't look at human beings, but we use model organisms because they allow us to do things to them which we can't do to humans. So we use C. elegans to understand development, or mice for all different types of experiments. Now, these obviously are not humans, and it takes energy and time, and it's difficult to transfer knowledge you get from C. elegans or mus musculus to human beings. But no one is going to say, stop working on C. elegans, stop working on mice because they're so different. We just say, okay, because they allow us to do particular work, which we can't do otherwise. We just take the pain and then transfer the knowledge we have there, and we look deeper. And in the same way, deep neural networks might not be as much as the human brain as you want, but they give you a unique way of doing things. You can start understanding them always better and better, and then you put additional transfer energy into transferring the insights into humans, as you do in our other domains of biological inquiry. Okay, so to summarize, here I've told you about 3 different ways how deep neural networks can be a useful tool for scientific explanation. We can actually use them akin to theory. And now I would like to go to the last part, where I talk about what I think is also a very big strength of deep neural networks, that they can be a starting point for new theories. It's actually good for exploration. So, people think about science as you predict and you explain, but it's another question of how do you come up with stuff in the first place? So the story goes like this. If you have a fully fledged theory, hundreds of years have been spent on developing how a particular things work, I don't know, gravitational mechanics. Then you derive hypotheses from this theory and you test them in experiments. And this is just the right way of doing it because your theory is very rich and you just need to find out how well it's doing. But it's okay. But what do you do if there is no fully fledged theory, or if there is actually no real theory at all? Well, I don't want to claim that for most cognitive functions, we don't really have a theory, but I would like to claim that these theories are not exactly perfect yet, right? It's not like we're filling the little blanks. It's what is visual cognition? Where is your theory? Could you please give me the book where it's written down how it works? And no idea. It's little parts somewhere or here or there and then big picture things which have never been really tested, which is totally fine. This is why neuroscience is so exciting. It's an open and new field, but it's also empty. So how do you go about, what do you do if there's no theory? How do you make progress? Well, what you do then is you just explore. You play around, you go new ways, you try stuff. Otherwise, what you already know is not enough to bring you intellectually to the next level. And deep neural networks can be very helpful there. And to make this point formal in philosophy of science, how this can be done, I would like to put this into different claims. And the first claim is that actually exploration generates new hypotheses that you can test. Okay, so it is not enough to only have crazy thoughts and think new stuff, but it also must boil down into something you can scientifically test well and convince the community. And how can this work? Well, to show you how this can work in one way is here exemplified by the concept of analogies, which was made by Mary Hesse, where she said that there's positive, negative, and neutral analogies between the stuff in the world and a model. And the positive analogies are the characteristics of the model that we know that the model and the target share. So for example, for our brains and our DNNs, we know that they both have simple discrete units like neurons or units or entities like neurons or units as computational building blocks. At this level, we know these two things are similar. Then there is negative characteristics or analogies. Like these are characteristics we know that the model and target do not share. Very simple. Brains are made of sugars, lipids, and proteins and water. They're biological stuff. And deep nets are made of silicium, or actually lines of code. That's where they are not similar. And then that's the important point. There is neutral analogies. There is the characteristics of which we do not know whether they are shared or not. And this is the potential for learning new facts about the target. So, the positive ones is you already know the two things are similar, you don't learn anything else. Negative characteristics is you know these two things are different, so again, you're not learning anything. But there's so many properties that are neutral right now, of which we don't know whether they are shared or not shared. And then there is potential for learning these new facts. So in this way, you can then generate a hypothesis and you can test it. And if you go to many conferences, there is, many to these neuroscience conferences or cognitive neuroscience, there's many posters which actually start or do delineate analogies and similarities between deep networks and the brain. And while this can seem tedious or derivative, it's actually what is being happening. New hypotheses are being found and they're being tested. The second way that they can help is that they can offer proof of principle demonstrations. Now, what is a proof of principle demonstration? It's a demonstration of the feasibility of a particular approach to a problem through the creation of an artifact that solves the problem. So the idea is, you have a particular idea how the world works, and then someone says, no, it can never work this way. It just can't. It's impossible because of this and this and that reason. And then you just build the thing and you show, look, it runs. And then the person say, it's impossible, it can't run, it can't work. But then you say, here, it's on my table, it's working. I showed you that it can work. So you have to revise your theory. So this is something from engineering where you basically prove your theory by building something that works according to this theory, which then disproves the other theory, although you have not directly disproved it. At least it proves yours that it's feasible. And this then motivates further scientific attention. And I think this is a funny reaction I also sometimes got, like in the very old days when I presented my deep neural network results. People just said, it can't be, it can't work. But what can you say to this? You just say, look at the slide. There's the code, there's the data, it works. So you have to revise your theories why it can't work. A good explanation for this is, for example, that a work from Jim DiCarlo from a bit far back, where he showed that a purely feed-forward network can predict neural activity in cortical area IT well. So here you see, basically how well things predict on the y-axis. On the x-axis, you have ideal observers, you have control models, basically different types of models. And on the right in red, you have different layers of a deep neural network. And then you see the deep neural network is predicting most variance in this region. And the important point here was that it demonstrates the feasibility of a purely feed-forward solution. So if the question is, okay, do I need a particular type of model, for example, that needs recurrence to explain brain activity? You can say, well, maybe yes, but look how far you can get with a much simpler model. It already brings you 50% of the variance, more than any other model ever existing. Now, this does not prove that the brain does it like that, and it doesn't prove that the brain is not using recurrent processing. It actually does, and it's also proven, but it shows you how far you can get with pushing into one particular direction, proves the feasibility of your approach. And again, I think in this way, deep networks can be very helpful. The third claim is, and now it's becoming that's a bit of a funny point, that it helps you to assess the suitability of the target. So the usual way how things work is you have a phenomenon in the world that you want to explain, and then you build a model, and then the model doesn't work very well. So you improve the model so that you increasingly well fit the thing in the world. If in our case, you have a particular behavior, you have a particular brain region or some activity, and you're going to change your model increasingly such that it's going to be a better model of the world. However, that's only half of the story, because actually modeling by itself can change what you are modeling. Because what you're modeling in the world depends on how you conceptualize it. And modeling by itself can change how you basically cut out the world. To an example, let's say you want to explain visual object categorization, or let's say visual cognition. And you believe that visual cognition is a particular set of cognitive functions, and you try to model them. And then you model around, and then you find out that your model actually does a lot of other things, which are kind of funny. And then you think, maybe I should revise my view of what visual cognition is in the light of what my model is doing. And maybe this is an example of how things like that happened. So this is again data from monkeys, where we're looking at explaining brain activity. And here you can see how well a deep neural network explains the category or categorization in a network in this particular region. And it makes a lot of sense that the early regions don't explain it well, and the later you go in the deep neural network, the better it explains it. But the authors found this, and then they thought, okay, this is probably so because we are losing information, as I told you in the beginning, about the location of the object. So if you want to have something that categorizes a cup as a cup, whether this cup is here or the cup is there, doesn't matter. So once you have an algorithm that actually recognizes cup independent of here or here, it should have lost information about where in the world this cup was. And then they actually checked this and found, no, this is not the case. Actually, in the model, with increasing layers, you not only get an increasingly better categorization, you also get increasingly better at knowing where this thing was shown in the world. And I thought, that's funny. So now we're going to record brain data in monkey and see whether this makes sense. And they found, yes, it is. So if you go from before to IT, it's following the deep neural network. The more you go up in the hierarchy of the visual system, the better you're in categorization, but the better you also become in finding out where this thing is in space. So basically, you had a prediction of the model from previous, let's say, research. You played with the model, found something that was really weird. Then you tested it in the brain, and you found, whoops, what this region is doing is different from what we believed it's doing. So it's changed the concept of what we think that this particular region is doing in the brain. Just, you have a model that does something, you play around, it behaves funny, you find out the brain behaves as funny as the model, and then you change your view of what actually the brain is doing. Now, this all being said about exploration, I think there are some caveats to keep in mind. One is that when we talk about prediction explanation, the standards are not pretty clear. They are a lot clearer than when you talk about exploration. So the standards and benchmarks to judge the quality of success in exploration are less well developed and explicit because modeling precedes fully fledged theory. So once you have a theory and you have a fallback from where you can judge how things work or don't work, it's easy to say whether one approach is better than the other. In a situation when you're playing around, this is much harder because you don't have these clear theoretical criteria. So there I would say, we should give deep networks the benefit of the doubt to avoid curbing the development prematurely. So although we cannot often judge whether this exploratory practice is better or worse or worthwhile, let's maybe just do it for some time to see where it goes. The second point is that you can use the very same model for an explorative purpose in one context, and you can use it for explanation in another. I told you about 3 different ways. There's certainly more in how you can use these models for explanation. So all you should do is then clarify in the papers how you use the model. Are you using it for exploration? Are you using it for prediction? Or are you using it for explanation? And then it's just fine and dandy how you do it. We just have to be explicit about how we do it. I think what is not fine to do is to write explanations like this. It's like this provides an explanation, but it's not a real explanation. People do this sometimes in paper, and DNNs provide explanations. I have no idea what this means. We're doing science here. Either it's an explanation and you tell me how, or it's a prediction and it's not an explanation. Just be clear about what it is, because like analogies or metaphors is not the right thing to use in scientific language. And third, of course, there's always the danger of mistaking the model for the world. So there's people who would like to stop looking at brains and spend their life only analyzing deep neural networks, which I think is totally fine, as long as you understand that modeling must always be checked by experimentation. So at some point, you must go back to the brain and you must check what you find out is useful or not. Otherwise, there is a danger that you're doing something which doesn't have its reflectance in reality. I would like to sum this up now. I've talked first about model nature, how scientific models are used. I've made the point that models are plural, diverse, and their origin doesn't matter. The plurality idea was that there's trade-offs between the desiderata, both theoretical and non-theoretical. So we will always need many models. The point about diversity was that the coexistence and the success that we see in all branches of science of diverse models kind of suggests that deep neural networks will be one important model, but it won't become the one Uber model, but it will just take its one place it has. And third, I've argued that the origin doesn't matter where it comes from. It just matters what role it plays for prediction explanation. Now, then I've talked about the 3 ways how models can be used for prediction, explanation, exploration. I've said that in prediction, deep networks can be used as tools to reach a practical aim. Think about the example of the prothesis or how to control experimental design. I've also told you about how it can be used going towards explanation as benchmarking. For example, by selecting models which do good, or by comparing models to understand what it is about these models that do best or that do good, makes them do good. In the third part, I've talked about the explanation, how these things can actually provide explanations with 3 different types of ways. Either you could say, they provide a different type of explanation, theological explanations, or you could say it provides the exactly same type of mechanistic mathematical explanations, but on a different level with different parameters. And finally, that they might be opaque, but they have very high potential for post-hoc explanations just by being nice to investigate. And finally, I've talked about exploration, trying to draw attention to the fact that science is not only about prediction explanation, it's also about finding new stuff, about playing around and modeling. And there I've tried to make the point that deep neural networks are particularly good points for new theories, because they allow you to generate new theories via neural analogies. And because they are such complex and rich and difficult models, that's why they are such a rich ground for new analogies. I've tried to show you how you can use them as proof of principle demonstrations. Basically, if you can show that these things work like this, then under these minimal assumptions, the brain might also be able to exactly do it like this. You know, it's just possible. You don't need something extra that other people believe that it's necessary. And third, it also allows you to assess the suitability of the target, which is a very particular case when you don't have a fully fledged theory, but you're actually sharpening up the concepts that you're using in science.